The idea this evening is that you are to pretend to be Caltech freshman students in Physics 1. You'll want to know how Caltech students behave so you'll know how to play your part. But let me tell you how they behave. For one thing, they laugh at my jokes. They also hiss at puns. And they applaud when the spirit moves them. I'm not going to write down any equations tonight, but I've put some of my favorites from Physics 1 up here on the blackboards just to remind us that there's something serious behind all this. What I'd like to start with instead is a demonstration that's of great importance to society. I'm going to show you how to extract energy from an unconventional source. This looks just like an ordinary lemon. And as a matter of fact, it is an ordinary lemon. What I'm going to do is to extract enough electrical energy from this lemon to run this little motor. And the first thing I have to do is to make sure that it doesn't get away. I can't help thinking that Julia Childs would find a better way of doing this. Okay, now, I'm going to use this as a battery, and these two nails are going to be my electrodes. And in order to show you that it really is a battery, I'm going to connect it first of all to a device that I have here. This device is called a galvanometer. I'll say something about how it works later. But it detects small electric currents. There's a laser here. The beam from the laser hits a mirror in there and reflects up on the screen that you see to the right. That spot of light at the 0 on the scale is the reading of the galvanometer. When I connect my galvanometer to the battery, which I'm just going to do now, that spot of light will deflect all the way over to the right to show that the battery is alive. Like that. Now, unfortunately, I can't run the electric motor just by connecting it to this battery because the lemon is not very well designed to be a battery. It's very well designed to be a lemon. The trouble is that although I can get electrical energy out of the lemon, it comes out very slowly. So I'm going to have to store it up. And I'm going to store it in these two cans here, which are called capacitors or condensers. I'll explain to you later what they are as well. But in the meantime, I'm just going to connect my lemon battery to those two condensers. When I connect the second condenser, the reading on the galvanometer will fall back to 0, like that. But then in the course of the lecture, it will slowly drift back to the right as those condensers build up charge extracted from the lemon. And later on in the lecture, there'll be enough charge to run the motor. And then I'll run it for you. The story that I want to tell you tonight began in the year 1543 with a timid monk by the name of Nicholas Copernicus. In that year, Copernicus published a book. The first copy of the book came off the presses. It was brought to him. He looked at it. He smiled. And he promptly expired. It was not an accident that Copernicus delayed the publication of his book until the end of his life. He did not want to face the consequences of what he had said. What Copernicus said in his book was, it would be a little bit simpler mathematically to describe what we see in the heavens if we imagine that the sun stood still and the earth rotated around it. Copernicus' book was published just a generation after the invention of the printing press. About 400 copies were run off. Of those 400 original copies of the Copernicus book, perhaps 100 still exist today. Scholars know the whereabouts of every one of those 100 volumes. They know who owns it, who's owned it in the past, who's written things in the margins, and what they've written. I have here one of those 100 precious volumes. Let me just open it to the frontispiece, and you can see here it says Nicholas Copernicus. At the bottom it says that it was published in Nuremberg. The year is 1543. In this particular copy, somebody has written in the side, to my loving friend George Thomson, it looks like. There's an inscription here in Greek. The inscription in Greek says, let only geometers, that is mathematicians, enter here. Copernicus didn't want the rabble reading his book. Actually, hardly anybody ever did read his book, but people knew what was inside. The title of the book, written down here, is On Revolutions, and it was about revolutions, real physical revolutions. it began the first great scientific revolution. As a matter of fact, when we speak today of revolutions, political revolutions, scientific revolutions, any other kind of revolution, we are speaking metaphorically of Copernicus' book and the effects that it had. Inside, I have marked a page on which there is a famous diagram by Copernicus of the new Copernican universe, with the sun at the center and the Earth merely the third planet out. Copernicus published his book, it came out, and then there was silence. For 50 years, nothing happened. And then, towards 1600, quite suddenly, there arose two passionate Copernicans in Europe. Their names were Johannes Kepler and Galileo Galilei. In the 16th century, there was no connection between mechanics and astronomy. Galileo studied mechanics, the science of the motion of bodies on Earth. Kepler studied astronomy. Johannes Kepler was of frail health. He was unlucky in love. He had an open, friendly nature, but was easily insulted. He suffered fits of depression and flights of exuberant enthusiasm. He was introspective. He was ingenious. In short, if he were alive today, he would be a Caltech student. Galileo was haughty, vigorous, arrogant, combative, selfish, and utterly brilliant. If he were alive today, he would be a Caltech professor. Galileo concerned himself with a simple question which was embarrassing to Copernicans. The question was, if the Earth really moves, why don't we fall off? It's a problem that still seems to disturb some people. Galileo studied the motion of projectiles. By studying projectiles, he could not only get at the fundamental scientific problem that he was interested in, he could also do a little military consulting on the side. He found that the behavior of any projectile on Earth could be understood by applying simultaneously two great laws. One was the law of falling bodies. The law of falling bodies says that all bodies, regardless of their mass, fall to Earth at the same rate. The other one was the law of inertia. The law of inertia says that once a body is in motion, it remains in motion unless something interferes with it. Galileo was born into the world of Aristotle, of Aristotelian physics. This here is a little Aristotelian world. In the Aristotelian world, a body moves only if it's pushed, and it stops moving the instant you stop pushing it. This particular world, though, I can change from an Aristotelian world into a Galilean world at the flip of a switch. Now, if I set the body in motion, it keeps on moving until something interferes with it. This is the principle of inertia. This is the world of Galileo. A little bit later, it was discovered that bodies could exert forces on each other without touching. That's an important discovery, too, but it comes a little bit later. Out of fairness, I should mention that Galileo never really got the principle of inertia completely right. That had to wait until René Descartes. But I don't like to mention that early in the year to the students. It's a matter of putting Descartes before the course. That shows promise. Galileo worked out the consequences of his ideas by means of thought experiments. He never really did the experiments that he suggested because he didn't have to. He knew what the results would be. But he argued about them. He thought about them. One of his thought experiments was to imagine what would happen if somebody on a sailing ship, which is sailing along, at the top of the mast of the sailing boat were to drop a ball. The question is, would the ball fall straight down towards the center of the Earth, or would it move along with the sailing ship as the sailing ship moved along? To an Aristotelian, the answer was very clear. In Aristotelian physics, anything that's dropped must fall directly towards the center of the Earth. But Galileo said, no, that's not what would happen. What would happen is that the ball would continue to move along with the sailing ship as it fell, so it would fall parallel to the mast of the moving sailing ship. To the Aristotelian, the ball should have fallen straight down while the sailing ship sailed out from under it. I wanted to do that demonstration here for you this evening. I wanted to bring a big sailing ship in with a tall mast and get up on top of the mast, but the physics department wouldn't let me flood this room so that the boat could float. So what I have to show you instead is a movie of that experiment. There's a fellow running by to show you the speed at which things happen. The boat goes by, the ball falls, and there it is, just as Galileo said. Now that went by pretty fast, so we have an instant replay. You'll see the experiment done 3 times. The first time it will come out the way Galileo said, the second time the way Aristotle said, and the third time the way Galileo said, so Galileo will win. Here comes the sailing ship. The thing to watch is the stripe on the hull of the sailing ship. It's directly below the point where the ball is dropped. The ball is dropped, it falls straight down parallel to the mast with the ship sailing along, past the stripe, and into the water. Now to show you what would have happened if Aristotle had been right, we'll tip the ball off a standing boom so it doesn't share the motion of the boat. Now the boat sails out from under it while it falls parallel to the boom, to the support of the boom. We'll do it one more time, showing you what Galileo meant. This time we pick up the ball from the boom, carry it along so it picks up the motion of the boat, and now we drop it. And it falls straight down along the mast, past the stripe, into the water. That was Galileo's thought experiment. I have one other demonstration that I'd like to show you to illustrate the combined effects of the law of falling bodies and the law of inertia. The problem is this. Suppose a hunter goes out to hunt monkeys. Now, you'll want to know why any hunter would want to go out and hunt monkeys. Please don't ask me that question. This is not a course in ethics, it's a course in physics. The hunter goes out to hunt monkeys, and he sees a monkey in a tree. We have a monkey in a tree right up there on that wall. Now he knows that when he shoots the monkey will see the flash from the gun, be frightened, and leave go of the tree. So the monkey will actually be falling, and he has to shoot the falling monkey. The question is, where does he aim? Does he lead the monkey aiming below it in order to lead it so the monkey will fall into the bullet? The answer is no. He should aim the gun directly at the monkey. The reason is because the monkey and the bullet are both falling bodies. Even when the bullet is going on the upward part of its arch, it's actually falling at the same rate as the monkey, and so if he aims directly at the monkey, the two will intercept in midair. That's what I'm going to show you. Now here's my weapon. This is a laser, and the beam from the laser runs along the sights of the weapon. Perhaps you can see where it hits my finger at the sights, and then runs up and hits the monkey up there in the nether regions, as you can see. This is a ballistic missile. The weapon, therefore, is a laser-guided ballistic missile. We will not be able to do this demonstration anymore if they sign the SALT II agreements. Okay, the gun is aimed directly at the monkey now, and when I shoot the gun, the monkey and the missile are supposed to meet in midair. I have to tell you, this is one of these demonstrations you have to practice a lot to get right. I have practiced this demonstration many, many times, and I assure you, I have never once hit that monkey. He is perfectly safe. That's why he volunteered for this job. Okay, you ready for this? When I pull the trigger, the monkey will fall from the tree, the missile will go off, and I'm supposed to hit him. Here we go. We got him. The work of Galileo and Kepler culminated in the giant figure of Sir Isaac Newton. Newton was born to a thoroughly undistinguished family of yeoman farmers in 1642. He was born both posthumously and prematurely, too late and too early. His mother soon realized that he was too lazy to be a decent farmer, and so she did the only thing she could. She sent him to the university. He graduated from Trinity College, Cambridge in 1665. 1665 was a plague year in Cambridge, and so Newton retired to the family farm in Lincolnshire. And while he was there at the farm in Lincolnshire, an event occurred which has become part of our folklore. He saw an apple fall from a tree. Yeah, this will hold you till dinner. and he invented the law of gravity. There was a serious scientific problem behind that legendary event. Newton believed that the Earth exerted the same kind of force on the moon that it exerts on the apple. The question was, if the apple falls, why does the moon stay up in the sky? I would like to show you how Newton reasoned. He said, let's imagine we have a cannon on a tower 16 feet high. If the cannonball simply rolls out of the mouth of the cannon, then it will behave just like the apple. It will fall straight down, and according to the law of falling bodies, it will fall 16 feet and hit the ground in 1 second. On the other hand, if we fire the cannon horizontally, according to the law of inertia, it will move horizontally at a constant speed while it's falling. But still, according to the law of falling bodies, it will hit the ground in 1 second. That's what determines its trajectory. If we fire the cannon harder, it will fly further in the horizontal direction, but it still hits the ground in 1 second. That continues to be true unless we fire the cannon so hard that it actually finds out that the Earth is curved and not flat. If that happens, it has further to fall, and therefore takes longer to hit the ground and is in the air for a longer time. As a matter of fact, we could imagine firing a cannon so hard that the ball will keep falling forever and never hit the ground. That, said Newton, is what the moon does. The moon goes around in its orbit, held in place by the force from the Earth. If at any instant the force from the Earth were released, then according to the law of inertia, the moon would like to fly off in a straight line. The force from the Earth instead makes it fall, keeping it in its orbit. The amount that it falls is shown by the red arrow. Newton set out to calculate how far the moon ought to fall in each second. He said, the apple falls 16 feet in 1 second. The moon, he knew, was 60 times as far away from the center of the Earth as the apple is. He thought the force making the moon and the apple fall should weaken as the square of the distance, so it should be weaker at the moon by a factor of 60 times 60, or 3,600. The moon should therefore fall each second 16 feet divided by 3,600. That works out to 1/20th of an inch. He then calculated how far the moon actually does fall each second. All he needed to know was the size of the moon's orbit and the fact that it goes all the way around that big circle about once a month. From that, he could figure out how long that red arrow would be for each second, and it turned out to be just 1/20th of an inch. That moment, when Newton found that his theory had predicted correctly just how far the moon falls in each second, that was the magic moment in human history when the physics of the heavens and the physics of the Earth became united in one science. Newton was 23 years old when he went to the family farm in Lincolnshire in 1665. He stayed there for 18 months. That period of 18 months was the most productive period of his life. In many respects, he spent the rest of his career working out the details of the ideas that he had then when he was 23 years old. His scientific output during his career was prodigious. He invented the differential calculus, the binomial theorem, the theory of colors, and much, much more. Above all, he combined the work of Kepler and the work of Galileo into the science of mechanics, a science which explains almost everything that we see around us in our ordinary lives. He also spent a great deal of time working on subjects that were less scientifically respectable. He worked on alchemy, biblical chronology, theology, history, and other arcane topics. He was a professional politician. He was twice elected to Parliament. He was named Warden of the Mint, and in 1705 he was knighted by Queen Anne and became Sir Isaac Newton. In 1696 he went mad. He quite literally went insane. It's thought today in retrospect that he may have been suffering from mercury poisoning. He recovered from that after a year or two, But even when he was sane, he was not very nice. During his career, he had bitter disputes over priority for scientific ideas with a number of his contemporaries, including Hooke and Flamsteed, and especially with Leibniz, whom he accused of plagiarizing the differential calculus. Poor Leibniz, who was entirely innocent of the charge, appealed to the Royal Society of London for justice. The president of the Royal Society, one Sir Isaac Newton, appointed a committee of avid Newtonians to investigate the question. And to make matters worse, he secretly wrote the report of the committee himself. The report did not look kindly upon Leibniz's claims. One of Newton's most famous remarks was, "If I see so far, it is because I stand on the shoulders of giants." Presumably he was thinking of Kepler and Galileo, but as you can see, he trampled on many others as well. After the time of Newton until our own time, the science of mechanics did not change very much. There were some improvements in the form of what we call conservation laws. That is, it was realized that there are certain quantities which never change, which always remain the same, which are conserved. The three great conservation laws in mechanics are the conservation of energy, the conservation of momentum, and the conservation of angular momentum. The conservation of angular momentum is what keeps spinning tops and gyroscopes from falling down. We have a demonstration that we usually use in this course to demonstrate the conservation of energy. We have a bowling ball hanging from a heavy steel cable that hangs from the ceiling. And the demonstrator picks up the bowling ball and walks over to one side of the room. Then he holds it up against his nose like this and leaves go of it. And it swings like a pendulum all the way across the room and all the way back up to his nose. But because of the principle of the conservation of energy, he knows that it can't swing back any higher than where he released it from. So even though he sees all that mass rushing at him, he knows that his nose is perfectly safe. That is, he believes that if he believes the laws of physics. Now, I have a firm principle against doing any demonstrations that are dangerous to the demonstrator. And that's why you don't see a steel cable hanging from the ceiling and a bowling ball here tonight. For the same reason, I found it prudent to be elsewhere on the morning when that particular lecture came up. And it was given by my associate, Dr. Barry Thomas. Fortunately, someone caught him with a camera just at the crucial moment. This discussion brings up another point. I have never understood why people keep telling us that we must conserve energy. Energy is always conserved no matter what we do. It's one of the fundamental laws of nature. I sometimes wonder if this energy crisis we keep hearing about might not be a breakdown in the laws of physics. Perhaps next week our president will come on television, look at us all sternly through the tube, and say, "My fellow citizens, we must all conserve angular momentum." Somehow I can't see that happening. The problem is not to conserve energy, but to conserve energy in useful forms, that is, to conserve fuel. Our fuel for this evening is lemon power, and we'll get back to that in a little while. First, I have to introduce you to the subject of electricity. In Newton's time, electricity was a curiosity. A typical experiment in the time of Newton was to take a charity boy, a street urchin, suspend him from the ceiling by silk threads, charge him up with an electrostatic charging machine, and draw sparks from his nose. I wanted to do that demonstration for you tonight, but the physics department was unable to procure any street urchins for me. This is static electricity. If I rub this rod with this piece of fur incidentally is a cat's fur. There is a naked cat in the back room shivering, waiting for the lecture to be over. If I rub the rod with the cat's fur, it gets charged up and it's capable of picking up little bits of paper. That's electrostatics. That was about the status of electrostatics, of the study of electricity, until one day in 1745 at the University of Leyden, where Petrus von Muschenbroek was doing an experiment. Muschenbroek thought that electricity was a fluid, and he wanted to make a solution of the electric fluid with ordinary water. So he had a technician, and the technician held in his hand a jar of water. And he put into the jar of water a stopper that had a long nail in it that went down into the water. and he held the nail up to the pole of an electrostatic charging machine so that the electric fluid would run from the machine down into the water and make a solution. When the technician grabbed the nail in order to remove it from the solution, he made a shocking discovery. Muschenbroek was not deterred. He simply hired another technician and pressed on with his research. It was soon found that the technician's hand could be replaced with a conductor on the outer part of the bottle, and the water could be replaced by another conductor on the inner part of the bottle. This became known as the Leyden Jar, and it was capable of storing electrical energy, storing electric charge. In order to store electric charge, it doesn't even have to be in the shape of a bottle. It can be in the shape of a can. These cans, these capacitors or condensers, are later-day versions of that same Leyden jar. Once armed with Leyden jars, 18th century electrostatic charging machines became potent devices. I have one here, which is armed with Leyden jars, two of them, one on each side, and I thought I would show you how it works in the hope of sparking your interest. You're getting to be pretty good at that. At this time in the 18th century, there were a number of scientists studying electricity, electricians. They would do experiments, and then they would publish the experiment, and everybody else, all of the other electricians, would read the paper and then repeat the experiment. It was a sort of a fraternity. And like all fraternities, it had its rituals, its rules. And one of the rituals was that every electrician prided himself on his ability to judge the amount of electricity he had created by feeling the shock. Before the invention of the Leyden jar, that was perfectly harmless. But when the Leyden jar came along, that changed dramatically. It nevertheless was part of the ritual that every electrician had to feel the shock. And so every electrician was obliged to feel the shock of discharging the Leyden jar. It was not a very pleasant time to be an electrician. Nevertheless, they all did it, with one exception, a German electrician by the name of Winkler, who gallantly permitted his wife to do it for him. He reported that she was unable to walk for a week. The first serious theory of electricity, the theory that succeeded in explaining how and why the Leyden jar worked, came from the most unexpected conceivable source. It came from across the ocean, from the edge of the American wilderness, from an unschooled printer by the name of Benjamin Franklin. I have here a portrait of Franklin that you ought to recognize from when you paid your contribution to the Associates. Franklin, of course, is well known for his experiment with the kite and the thunderstorm. That experiment made Franklin world famous. It also served to show that electricity was no mere laboratory curiosity, but rather one of the fundamental forces of nature. Before Franklin's time, a lightning storm was a frightening thing. When a town found itself in a lightning storm, it would typically have the church bells rung in the hope of scaring it away. Unfortunately, the lightning tended to strike the church bells, run down the damp bell cord, and dispatch the bell ringer. Franklin's invention of the lightning rod not only saved a lot of bell ringers, it was also the first demonstration that basic research in pure science could lead to control over the forces of nature. We tend to think today of Benjamin Franklin as a diplomat and statesman who dabbled on the side in scientific experiments. But that's not true historically. Historically, the opposite is true. Benjamin Franklin was a world-famous scientist who, at the end of his career, dabbled in politics. The next hero in our story is Alessandro Giuseppe Antonio Anastasio Volta. Volta's father was one of four brothers, all four of whom were priests. If that situation had continued, we would have called the Volt something else. After 11 years in the priesthood, the father stepped down to propagate the family name, which he did a very good job of because we're still using it. His marriage produced 3 priests, 2 nuns, and Alessandro. That was birth control Italian style. Alessandro himself was not cut out to be a priest. His contemporary scientist Lichtenberg said of him, Alessandro understood the electricity of women. Just as Benjamin Franklin had set out to show that lightning was the same as ordinary laboratory electricity, Volta set out to show that animal electricity was the same as ordinary laboratory electricity. Animal electricity was manifested in the electric eel. Volta wanted to build an artificial electric eel. What he wound up doing instead was inventing the electric battery. And that brings us back to our lemon battery. Now, the idea is this. When I push down this switch, we'll discharge the condensers. It should run the motor, and at the same time, the reading of the galvanometer should drop back down to 0 to show that the stored electricity is being discharged. Okay, are you ready for this? Here we go. There it is. Lemon power. The next discovery to be made was the connection between electricity and magnetism. Throughout the 18th century, people suspected that there was some connection between electricity and magnetism, but nobody could prove it, could find the connection. There were intriguing hints. For example, there were persistent reports by the captains of sailing ships that their ships' compasses behaved peculiarly in a lightning storm. Now, I'd like to show you how that must have looked. Imagine that you're the captain of an 18th century sailing ship watching your ship's compass on television. The compass that we're looking at is right down here between the poles of our lightning machine, and we'll see what happens to the compass in the vicinity of lightning. But you have to remember, there's a storm. If there were no storm, there'd be no lightning. So the ship is tossing back and forth, and the magnet is bouncing around, and there's water, there are waves washing over the gunnels, or whatever it is that waves wash over. And then the lightning comes along. And we observe that something, in fact, does seem to happen. But is that a direct effect of electricity on the magnetism of the compass needle? Or is it simply an electrical effect due to the fact that the compass needle is not only a magnet, but also an electrical conductor? In order to find that out, one would have to repeat the experiment carefully and manipulate things, change things, in order to see which was true. That experiment of observing the compass in the lightning storm is unrepeatable. You can't repeat the experiment to find out what really happened. These sightings of the effects of lightning on the compass needle in the 18th century are a little bit similar to sightings today of UFOs by airline pilots. They may be interesting, but they are not scientific data. The actual discovery was made 20 years after Volta's invention of the voltaic pile, the electric battery, in the year 1820 by Hans Christian Ørsted. The story that we're told about that discovery is that he made it accidentally during a lecture demonstration. That's a particularly ironic story because what really happened was that he purposely made the discovery in front of witnesses so that nobody would ever think that it had happened by accident. Now, I wasn't at that particular lecture, so I don't know exactly what happened, but I would like to try as well as I can to reconstruct the way it might have happened for you. So let us set the stage. The year is 1820. We're in Copenhagen. It's the evening, and you are a glittering audience of the elite of Copenhagen society. Ladies in evening dresses, gentlemen in frock coats. And I am Hans Christian Ørsted. Brilliant thinker, but a bumbling, inept experimenter, and very nearsighted. Now, I understand this is all a little bit unrealistic. I'm not nearsighted. But we'll just do our best to see what might have happened. We have here a voltaic pile, just invented 20 years ago. This one made for us by Sears. And we're going to use that to run an electric current through this bar. Now, Ørsted's reasoning was this. When you run an electric current from one of Volta's batteries, the electricity tends to turn into something else. Electricity running in a current turns into heat. If the current is stronger, it turns into light. And he thought if you made a current that was stronger still, it would turn into magnetism. So to show that, he set up his experiment so that he could have the current from the battery running through a rod like this, and below the rod is a compass needle. You can see the shadow of the compass needle up on the screen. He has the rod disposed perpendicular to the compass needle. The idea is that when he runs current through the rod will turn into a magnet, and the magnet will make the compass needle swing around and become parallel to the rod, and then he'll know that he succeeded in creating magnetism. Now, as it happens, I need an assistant for this demonstration. Sir, would you please serve as my assistant for this demonstration? Now just put your left hand on the switch and face the television camera. And don't worry, this will all be over so fast you'll never feel a thing. When I tell you to, you just pull the switch down towards you when I tell you to. All right, so let's review what's going to happen. When we pull the switch down, the current will run through the rod will turn into a magnet, and the magnet below it will swing around and become parallel to it, and we'll have discovered electromagnetism. Are you ready for this? Okay, go ahead. Throw the switch. And absolutely nothing happened. You better open the switch. Well, poor Ørsted was very disappointed, of course. So he tried to figure out what had gone wrong. Well, he figured maybe it was because the rod doesn't have poles on it like a magnet does. So he took another wire and connected it to the battery, and he made a kink in the wire to act like a pole, and he tried to use the kink to attract the compass needle, but it didn't work. Nothing he could think of would make the compass needle budge. And so finally, disappointed, he gave up and dismissed his audience. The audience started filing out of the room, and while they were doing that, his assistant informed him that he still had a little bit of charge left in the battery. Well, that was not something to be wasted in 1820, so he decided to try one more thing. It made no sense at all, and that's why he hadn't tried it before. What he tried was putting the bar that he was running the current through parallel to the magnet needle. That way, even if the bar turned into a magnet, nothing would happen. That's why he hadn't tried it. But he decided that he would try this because there was nothing else to do, so he asked his laboratory assistant to throw the switch once more, and he threw the switch once more, and the magnet swung around. Even the president of Caltech can make a lecture demonstration work. He, of course, had not dreamt that the current would turn into a magnet perpendicular to itself, to the direction of the flow of the current. Incidentally, what we've just seen is also the principle of the galvanometer with which we saw the electricity from the lemon. Inside of the galvanometer, there is a small magnet which deflects when a current passes through some coils nearby. The mirror is attached to that magnet, and we see the deflection up on the screen. When Ørsted's discovery was made and published and the word got around about what Ørsted had discovered, every scientist working on electricity at the time knew immediately what the next great discovery was going to be. Ørsted had discovered that you could make an electric current act like a magnet. The next discovery would be to find out how a magnet could be used to create an electric current. Every scientist knew that that was going to be discovered and knew that whoever discovered it would be immortal. All of them wanted to be immortal, and so every one of them scurried back to his laboratory and got to work to make the next great discovery. And nothing happened. 12 years passed before the discovery was made. Now, 12 years is a very long time. 12 years is more than 2/3 of your lives. It's nearly half of my life. And when it finally happened, 12 years later, that the discovery was made, as so often happens in science, it was made not once but twice, independently by two different people in different parts of the world. The discovery was made in the United States by Joseph Henry, and in England by Michael Faraday. The discovery was this. I have here a loop of wire connected to the same galvanometer that we were using before, still red up there on the screen. This is just simply a loop of wire. There's nothing in this circuit that could run a current and deflect the galvanometer. And I have here an ordinary ball magnet. And I can make a current run through my ball magnet simply by passing, a current run through my loop of wire simply by passing the ball magnet through the loop. Watch as I do it on the screen. You see, there's the current running on the screen. If I pass the loop through the magnet, or the magnet through the loop, it makes a current run. This discovery, called electromagnetic induction, is really the basis of all of our present technological civilization. Yes, do you have a question? Nope, it has to be changing. If I put it in and leave it there, it just comes back to rest. Only when the magnetic field is changing around the wire does a current flow. I'd like to show you another effect, an indirect effect of electromagnetic induction. I have over here a pendulum. The pendulum has at the end of it a copper slab. And when the pendulum swings, it swings between the poles of an electromagnet, which is now turned off. If the electromagnet were on, then as the pendulum swings into the poles of the electromagnet, it's moving into a region where there's a strong magnetic field, just as the wire was moving into the region where there was a magnetic field with a ball magnet. At that point, electric current is induced to flow around in the copper slab. Now, when an electric current flows through anything, it turns into heat. And heat is a form of energy. And by the law of conservation of energy, the energy must come from somewhere. And where it comes from is the energy of motion of the pendulum. So when I turn the magnet on, it will make the pendulum slow down. And I want you to see that effect. So we'll get it swinging. And what I'd like you to do is to watch it swing a few times. Let me get it swinging a little further. Watch it swing a few times so that you sort of get the rhythm. So that when it changes, when it slows down, you'll notice that it's slowed down. I'll turn the magnet on here. And there it goes. I hope you noticed that. The co-discoverer of electromagnetic induction, Michael Faraday, was one of the great scientific geniuses of the 19th century. When Faraday was a young man, here is a picture of Faraday as a young man, he was apprenticed to a bookbinder. That was destined to be his career. He had no formal education, just as Benjamin Franklin had no formal education. He remained throughout his career mathematically illiterate. He could never understand mathematics. He could not read the scientific papers of his competitors because he could not understand the mathematics. He nevertheless consistently made the key discoveries throughout most of the 19th century. While he was apprenticed to the bookbinder, he started in the evening attending lectures at the Royal Institution in London given by the great chemist Sir Humphrey Davy. Faraday was enthralled by Davy's lectures. And he went to Davy and he begged Davy for permission to work at the Royal Institution in any capacity whatsoever. He would have been happy as could be just to be permitted to sweep out the laboratory. Here's the laboratory he wanted to be permitted to sweep out. Davy definitely needed help. Here is a page from Humphrey Davy's notebook. I'd like to read to you what it says on that page. It says, objects much wanted in the lab of the Royal Institution. Cleanliness, neatness, regularity. The lab must be cleaned every morning. Then we lose some because of the ink blots. And it continues below, these must be in the laboratory. Pen, ink, papers, and wafers. And they must not be kept in the slovenly manner in which they usually are kept. I am now writing with pen and ink such as was never used in any other place. Michael Faraday did much better. Here is an example of Faraday's calligraphy. The spelling leaves a little bit to be desired, but the calligraphy is just fine. Davy took on Faraday and allowed him to sweep the lab. After a while, he allowed him to take notes while Davy was doing his experiments. Later, he even allowed Faraday to do the experiments himself, and it soon became clear that Faraday was a natural genius. Eventually, Faraday took over and became himself the professor at the Royal Institution. He not only became a celebrated scientist, he also became an accomplished lecturer. This is a woodcut of Faraday delivering at the Royal Institution a lecture in the same tradition of evening lectures as the ones he himself had heard from Humphrey Davy. This particular occasion was deemed worthy of making a woodcut of because it was attended by the Prince of Wales. It's remembered today because the lecture was delivered by Michael Faraday. Faraday was one of the first scientists to live in the age of photography. He's one of the earliest scientists of whom we have photographs. Here are 4 of them. Faraday's output throughout his scientific career was immense. From early manhood until old age, from early morning until late at night, he worked and worked and worked and produced scientific results. One can't help wondering what drove a man like Faraday to work so hard and so long. Why didn't he relax a little bit, take some time off, spend some time with his family? We can see the answer to that question in the next slide, which is a picture of Michael with his wife, Sarah. I have just one more demonstration that I would like to show you this evening. This demonstration is in honor of Ernest Watson. The invitation that you received to come to this lecture this evening had on it this picture of Ernest Watson delivering his celebrated lecture on cryogenic fluids here in this room, 201 Bridge, many years ago. Watson's evening lectures were in the tradition of the lectures given at the Royal Institution by Faraday and by Davy before him. Today's Watson lectures at Caltech are in that same tradition as is this lecture this evening. Now, I never attended one of Watson's lectures, so I don't know exactly what he did, what properties of cryogenic fluids he showed, but I'm going to show you one. I have here liquid nitrogen, and I have liquid oxygen. These are clear, colorless, and very, very cold liquids. They look very much alike, but their properties are quite different. Liquid oxygen, for example, is oxygen. It's chemically very reactive, and nitrogen is chemically not very reactive. But that's not the property that I want to show you tonight. The property I want to show you tonight is a magnetic property of oxygen. I'm going to switch the television monitor so you can see what's going on between the poles of this magnet right here. I'm going to pour first liquid nitrogen and then liquid oxygen between the poles of that magnet. First I have to turn the magnet on. It's now on. And if I pour liquid nitrogen between the poles of the magnet, the nitrogen vaporizes and becomes part of the air in the room, but the magnet doesn't do anything special to it. If, on the other hand, I pour oxygen between the poles of the magnet, the oxygen sticks there, held there by the magnetic force, unless I turn off the magnet, whereupon it falls away immediately. Oxygen is a strongly magnetic, what we call a paramagnetic substance. I won't be needing the rest of this stuff. I would like to end this evening's lecture the way the real lectures in Physics 1 actually begin. The physics lecture is the first lecture the students come to on their first day of classes. I considered it a very heavy responsibility to utter the first words that the students would hear in a lecture in their entire university careers. I thought for a long time about what those first words should be, and here's what I finally decided upon. There are certain kinds of human activity which can really be done anywhere, but which the mind associates with a particular place, where that activity is somehow more special, more elegant than it is anywhere else. For example, I'm not inclined to gamble, but if I wanted to gamble, I wouldn't go and play poker in some sleazy back room. I would fly to Monte Carlo, put on my tuxedo, and play roulette in the casino. Another example is tennis. The place to play tennis is Wimbledon. If you like horse racing, it's the Kentucky Derby. If you like opera, it's La Scala in Milan. And if you want to study physics, the place to study physics is Caltech. We are, all of us here in this room, gathered to study physics at Caltech this evening. You've been a marvelous audience. Thank you very much.
awfully quiet here. Very quiet. Well, it's just a college campus coming up to final exams. You'd expect it to be quiet. I mean, they'll all be in their rooms studying. Yes, we expect to find some strange situations as we gather stories for the pages of Discover magazine. But it is quiet. Almost like the calm before the storm. The students are in their rooms, all right. But they're not studying. They're preparing for this, Ditch Day, the day when Caltech students go a little crazy.
49 and 50 and 51. Where's the dot?
They're looking for clues. They're struggling with the strangest of tasks.
Yes! Yeah!
Just for the satisfaction of entering the senior students' rooms. It all begins weeks before when seniors start building their stacks, as they're called, behind the sheets. On the day, the underclassmen have to break through the stacks, sometimes literally. This door and the window are sealed with a brute force stack.
You guys should just hang it up. You'll never do it. Yeah, Greg, I think you might as well go work on something else.
As the seniors leave, the underclassmen go to work.
Stand back.
When they return this evening, will their stack have withstood the onslaught? Just the night before, the brute force boys were still building. But for months ahead, they'd been refining their plans.
We went over and talked to a structural engineer in the physical plant, and he calculated out the weight of this whole structure, and he estimated it to be 7,200 pounds. He also looked at the plans for the building to see how much weight the whole thing could take, and he estimated about 12,000 pounds. So it shouldn't fall through unless we jump on it or something.
As the seniors build, the underclassmen outside swap rooms.
We've got some hydraulic jacks that we can brace against the wall and just kind of inch it over to the door. And then we'll brace it in with some more jacks and brace the top with some jacks. And then we'll move over to the window where we've got some more of these concrete slabs here. And we've also got a steel plate. There's a 1/4-inch steel plate you can see back here, which will go in front of the concrete slabs.
They can't do the window as steadily as they do the door.
We can't work as much to the window as we can to the door.
There's really no way they're going to get into through the window. It's on the second floor, and everything they have to do is going to be from a ladder.
Everyone has a good time on Ditch Day, except for any careless senior who's caught on campus between 8 and 5. Wally Walters, a senior who won't get caught. And he doesn't like brute force either. The stack he's making is pure finesse. It's a very clever computer which will unlock his door only when it receives a code of 40 tones from this box, which will be outside the door. When the underclassmen try different tones, the computer replies with helpful hints.
Hearing 4 high notes tells me that there are 4 ones in the code.
It'll take about 3 hours of painstaking deduction to figure out the correct way to arrange the 12 different tones in the 40-place sequence.
There will be a short pause.
Ditch Day. Right away, the window, weak point of the brute force stack, is under attack.
We're going to take a crane and go up to the top story, take out the windows, take a huge diamond-coated saw through the step up there, and climb in.
Meanwhile, a crowd's forming around the mushroom stack. Wild mushrooms of different types have to be located using clues taped to the locked door of the seniors' room.
Right out front.
That's the mushroom.
Right by the...
Wait.
Got it.
What's the
number on it?
What's the number on it?
5 has a 9.
9.
5, 9. So that's
7G.
7G, 2J9.
The mushroom clues will unlock the secret of this strange device built by Roger Moulton.
When the underclassmen find the mushroom, they'll find a letter or a number, which arranged in a particular order indicates MDR 29970, my student account number on the computer at Caltech. If they look at my account, they'll find instructions of how to open my door.
Well, we're on his account. Let's take a look at his directory.
Maybe you're wondering where it's all leading. You might. When the electrolyte is complete, the positive wire will make contact to an explosive charge, will cause a tennis ball to be ejected through the cannon in the window. It is in this way that the key will be encouraged to leak.
The cannon will fire when this pool of mercury has been dissolved. The mercury is suspended on a rubber band. The right voltage dissolves the mercury, the band contracts, contact is made. Although there's a lot of serious science that goes into the stacks, Ditch Day has plenty of the more traditional student activities.
Change the orientation. Like, tilt it back a little bit.
Try less power.
The helicopter stack, being tried by a group outside senior Juanito Villanueva's room.
I'll leave a series of clues which will lead them to find a hole behind this letter T. And they're supposed to take a vitamin, drop it into the hole, and it will be carried by a tube leading from that hole to this area of the platform.
Toy. Vitamin.
Juanito demonstrates inside his room what the underclassmen will have to do from the outside. And then?
Small charges in the corners of the frame are set off, causing the frame to separate from the window. And their mission is completed.
It's on. It's flying.
Stop it!
A simple task? Oh no. Champion stack builder Juanito has complicated things.
Some way to control it. Are they doing anything?
You can only see into the room from a ladder or through the wall, but the helicopter controls are in the corridor. And to make things worse, whenever the helicopter is flying, a soundtrack drowns out any attempt at communication.
What?
About 11 o'clock. The brute force and the tones are going well. At the mushroom stack, they've connected the power, but is the mercury pool inside doing anything?
Is there enough light?
Back at the helicopter, a breakthrough with the observation problem. At the tones, they've got the code, but there's one sticky key.
Yes.
All right. Come on, click you.
Well, it's not going to give me... Hey! Yeah! I told you.
Oh, no. Oh!
Right, again.
Yeah!
And this is the traditional reward, a bribe left by the seniors to discourage any unfriendly counterstacking.
Doritos and some pop.
Just follow this, I guess.
Anybody want to start on a pie?
Yeah, come on down. Turn it. All right!
Yeah! All right. Yeah. Only took 3 hours. Go for it.
Holy crud. I am impressed.
1, 2, 3.
The brute force boys left no bribe, so their room is treated in the way they deserve.
We're having difficulty telling whether there's anything actually happening.
The mushroom stack. Is it or is it not working? The room key is in the tennis ball. Roger Moulton's bribe was not appreciated. Later, they locked him out of his room.
Donuts! We
Donut. We got a counter strap.
Wait.
At the helicopter stack, the challenge proved too great. So they climbed in and gave a little helping hand.
Congratulations, you successfully broken my stack. Area of my window. In about a minute and a half, you should be able to get in through the windows.
Uh-oh.
If nothing happens,
Get this guy away from the window.
Get
the window.
Well, we'll have to go take a look and see what happens.
Yeah, why don't you just, check out your room? We opened it for you.
5 o'clock. The brute force builders returned.
Did you even try to move this?
Yeah, we tried.
What did you say, Froggy? Hello?
Clean out the lounge.
But I think they really wimped out for one thing, going through the window.
But you guys didn't touch the door.
You'll notice the door is not even damaged.
Brothers is guest on Late Night America, all tonight here on KCET.
Smithsonian World is made possible by a grant from the James S. McDonnell Foundation of St. Louis, which supports significant programs in education, research to improve human life, and global understanding. Additional funding is provided by the Corporation for Public Broadcasting. The Secretary of the Smithsonian Institution surveys a dream, a new museum complex under construction on Washington's Mall. It will be known as the Quadrangle, a center for African, Near Eastern, and Asian studies. For 20 years from his office in the Smithsonian Castle, S. Dillon Ripley has guided and administered the national museums which constitute the Smithsonian Institution. He has seen the mall